question is, so a large bed of rocks are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules per gram degree Kelvin. So they're using Kelvin there, you'll notice, but Kelvin and Celsius are interchangeable in this particular type of problem because it's not important to know the absolute temperature. Whenever you're doing thermodynamic calculations that do require you to know the absolute temperature, then you're going to use Kelvin, because in those kinds of calculations, it's important to know that zero means zero energy. The zero that we use for Celsius is not zero energy. It's just the freezing point of water. But even a block of ice has heat in it. It's kind of a weird idea. But here, think of a thought experiment. If I took a block of ice at 0 degrees Celsius, or even at minus 20, it would be hard to handle, because at minus 20, your fingers would stick to it from just the moisture on your fingers. If you touched a block of ice at minus 20, it would temporarily melt on the surface, and then it would freeze again because the rest of the ice is colder than the freezing temperature of water. So your hands would stick to the ice that cold. But if you took that block of ice and put it into a tub of liquid nitrogen, which boils at minus 196, the liquid nitrogen would start boiling furiously because you're 176 degrees above the temperature of boiling nitrogen. Nitrogen boil, it's a gas normally at room temperature, but if you lower its temperature to minus 196, you'll turn it into a liquid. And to turn it into a solid, you'd probably have to go to minus 230 or something. Once you get to minus 273, nothing will be a liquid except maybe helium. Helium will stay a liquid right down to about minus 273 point something. It doesn't become a solid. I don't think they are able to get it to become solid because it's too close. The temperature for solid helium is too close to absolute zero. Mind you, don't quote me on this. That's partly why scientists are working so hard to find superconductors that work at temperatures much higher than absolute zero. If we ever do discover, and we are getting closer, if we ever do discover superconductors that work at temperatures above zero, that'll be revolutionary, because then it'll become possible to make an MRI, in the school, that kind of thing. You won't need superconducting magnets cooled with liquid helium. You'll be able to just plug the thing in and you'll be able to take an MRI, so your coach will be able to bring the machine onto the field if you've fallen down and see if your arm or leg bone is broken or something. It'll be that revolutionary in terms of advances in science. You'll have railway trains that will be floating, maglevs, magnetic levitation trains will be very much more accessible and easier to make. It would literally revolutionize, the same way the discovery of electricity revolutionized science. The discovery of a room temperature superconductor will have the same effect within about 50 years. Maybe you'll be lucky enough to see it when you're old yourselves. I'm hoping the progress of science sometimes goes faster than what you expect. There was an article I was reading that made me laugh because it was a headline from the New York Times in 1908. And it said, it'll take men 1 million years to achieve powered flight. 8 days later, Orville and Wilbur Wright achieved powered flight. So sometimes scientific projections are not what people think they're going to be. We discover things faster than we were expecting. Yeah, enough about small talk. Let's do this. B. Q is equal to MC delta T, yeah, in this case. And we're looking for the delta T when 450,000 kilojoules of energy is released by 50,000 grams of rock with a specific heat capacity of 0.82 joules per gram degree. So we're going to rearrange this equation to solve for delta T. So that's going to look like this. Q over MC is going to give you the delta T. And let's just put in all the numbers. 450 kilojoules times 1,000 joules per 1 kilojoule. All of that divided by 50,000 grams of the rocks. Remember to use the right units. The units have to match up, or else you're going to get you're going to get wrong numbers. 0.82 joules per gram degree Celsius. And the answer I got was 10.97560,976. Obviously, I'm not going to report that number. That's too many significant figures. You really shouldn't report more than 2 because you only have 2 significant figures here. So the answer comes out to, when you round it off, 11 degrees Celsius. So I put a little note here that says Kelvin and Celsius degrees are the same size, but the scales are offset by 273.16 degrees, so that 0 degrees Celsius is equal to plus 273.16 Kelvin. I remember once I was asked to do a demo at some mall. I forget which government initiative it was. Anyway, they give me a bunch of liquid nitrogen, and I was doing demos like sticking roses in the bucket, and then they would shatter like porcelain. Another really cool thing I did is I took a bunch of liquid mercury, and I stuck a wooden handle into the mercury, and then I immersed the whole thing in liquid nitrogen, and I made a hammer out of liquid mercury. Of course, the mercury freezes at -40, but if you cool it to -196, it looks like a piece of steel. And then I hammered a nail with a hammer made out of mercury, which was liquid a few seconds earlier. Another thing that I did was really cool is I took some surgical rubber tubing, the kind you use in those nice slingshots, the ones with the yellow tubing, and I cut the yellow tubing at an angle so it made a sharp point, and I dipped it with a string into liquid nitrogen. Then after it was nice and cold, I took the rubber and I hammered it into a piece of wood. It was that stiff. I could hammer a piece of rubber into a wooden plank, and then when it warmed up to room temperature, the little rubber piece was hanging limp, but stuck in the wood, which was pretty cool. So liquid nitrogen has some very useful applications. Like say if you want to put a gear wheel and a shaft together, you can machine the sizes to very tight specifications. And then what they'll do is they'll warm up the gear and they'll cool the shaft so that the shaft will shrink with the cold and the gear will slightly increase in size. And then you can slip them together. And when they warm up to room temperature, it's as if they're welded. They're super tight together. That would be one application, but there are many like that. You can take liquid nitrogen and put it on a piece of metal, cool the metal down to -196. And if you hit it with a hammer, it'll shatter like candy. Because a lot of metals become very brittle when they get to a very low temperature. So you can use that as a way of, say, shattering a lock or something. I don't know if I should be telling you this. Say if you lost the key to your bicycle lock, that would be one way to get rid of it. Well, there are probably easier ways, like just rent a grinder and grind it off. Anyway, the next problem you're going to do is page 186, practice example. Here's the question. When 50 milliliters, and I think I gave you this for homework, when 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar hydrochloric acid are mixed in a constant pressure calorimeter, the temperature of the mixture increases from 22.3 degrees Celsius to 23.11 degrees Celsius. The temperature increase is caused by the following reaction. So it's silver nitrate reacting with hydrochloric acid to give you silver chloride and nitric acid, aqueous nitric acid as a byproduct. Calculate delta H for this reaction in kilojoules per mole of silver nitrate used, assuming that the combined solution has a mass of 100 grams and a specific heat of 4.18 joules per gram degree Celsius. So let's start by writing what the chemistry looks like. This is practice example on page 186. We're going to use Q is equal to MC delta T. And the reaction is silver nitrate, an aqueous solution, reacting with hydrochloric acid, also an aqueous solution, and producing silver chloride as a precipitate. So we're going to put solid on that. And nitric acid will be a byproduct, but that's going to remain aqueous. It's a strong acid and it's quite soluble. you're going to use 50 milliliters of this, a 0.1 molar solution, and 50 milliliters of this. I like to do this when I set up a question. I like to write all the little parameters that are applicable to each chemical involved. That way it's all laid out for you. You can see what you're dealing with. I find it stressful to have to pick out the details of what's going on in the written question if it's all sort of spread out on a sentence. I prefer to put it all in a concise way on the paper that I'm writing the answer to. So it's not necessary to do it this way, but I recommend you do it this way because it helps to clarify your thinking. Now the formula to find out the number of moles of something is the molarity times the volume of the solution. So that's in units of moles per liter, and this is the volume of the solution in liters. And that's going to tell you how many moles. How many moles. That's just a refresher there for grade 11. And using N is equal to MV, we find that N is equal to the molarity of the solution, 0.1 moles per liter, times the liters of solution, 51 thousandths of a liter. So the liters cancel and you get the number of moles, which is 5.0 times 10 to the minus 3. Ditto over here, you get the same result, 5.0 times 10 to the minus 3. So the same number of moles of silver nitrate and hydrochloric acid are reacting. And we're going to now find out how much heat flux there was. The total volume of the solution is obtained by adding these two quantities. Remember, you're mixing them into each other, so the total volume now is going to be 100 milliliters, which is 100 grams, because we assume the density of water is 1. I don't know if we can do that. I forgot to put the camera on the right spot. Just remind me if I forget. You have it. You can't see it, but if you don't see me move the camera when I move board, you're going to get nothing. So Q is equal to MC delta T. Therefore, let's put the numbers in. 100 grams of solution total when you mix the two together. 4.186 joules per gram degrees Celsius. I think the book said 4.18. I put 4.186. Sorry, that's the way I did my calculation. So that's what we're going to go with. 22.3 degrees Celsius. So when you multiply all those quantities together, you get 339.066 joules of energy has been transferred from that reaction, or released from that reaction. And we can see it's going to be negative because it's going to be an exothermic reaction. It's going to generate heat. Now that's for, that energy came from this. Now this is the tricky part. Don't use 100 again. Now you're going to go back to the fact that this came from 50 milliliters of a 0.1 molar solution of silver nitrate. Or basically that many moles of silver nitrate generated this amount of heat. So that's what we're really interested in. So we're going to find that out. So 339, negative 339.066 joules per 5.0 times 10 to the minus 3 moles substance gives you negative 67,813.2 joules per mole. And let's put it into kilojoules. So we're going to say 1 kilojoule per 1,000 joules. That allows you to cancel joules. And it comes down to negative 678 kilojoules. You're only allowed 3 sig figs, so I did that for you as well. In the next problem, the heat capacity is used instead of specific heat capacity. So the formula is, Q is equal to MC delta T is not appropriate because
Mr. Alleluia in the building, please call extension 6001. Mr. Alleluia, 6001. Thank you.
Tell you they have that volume stuck on 11. So Q is equal to MC delta T is not appropriate in this case because you're not dealing with a mass and a specific heat capacity and a change in temperature. You're given a a heat capacity for the whole thing. So all you care about is the heat capacity for the whole thing times the temperature change. So you're gonna use Q is equal to C delta T in this case, in the next question. So the next question is not gonna fit here, so we're gonna do it over here. Come with me if you want to live. So, practice exercise on page 187. I've got chemistry on the brain here. So Q is equal to C delta T is what we're going to use in this case. Let's read the question. A 0.5865 gram sample of lactic acid is burned in a calorimeter whose heat capacity is 4.812 kilojoules per degree Celsius. The temperature increases from 23.1 to 24.95 degrees Celsius. Calculate the heat of combustion of lactic acid, A, per gram, and B, per mole. All right. So the heat capacity for the calorimeter is 4.812 kilojoules per degree Celsius change in temperature. Did somebody leave? So you're going to get 4.812 kilojoules per degree Celsius. And the temperature changes from 23.10 to 24.95, so we're going to find a positive number, and then we'll sign the sign. The sign convention is going to be negative because it's exothermic, it generates heat. So what you get is 4.812 kilojoules per degree Celsius times 1.85 degrees Celsius temperature change, so the degrees Celsius cancel. What you get is 8.9022 kilojoules of energy. Let's convert it into joules just for fun. And what we get is negative 8,902, I forgot to put the negative sign there, joules of energy. And I'm going to say negative sign because it's exothermic, meaning it releases heat. The reaction releases heat. Now, we found how much heat is released by that reaction, but we haven't found it per gram of reactant or per mole of reactant. So we're going to use that number again and divide it by the grams of the actual amount of stuff that was burned, and then that'll give us a per gram amount. So this is part A of the question on page 187. So negative 8.9022 kilojoules divided 0.5865 grams of lactic acid, and you get, after sig figs, 15.2 kilojoules per gram. Lactic acid, by the way, it was lactic acid, wasn't it? Yeah, lactic acid is a byproduct of metabolism. Whenever our muscles have to work under a load in which there's not enough oxygen being supplied to the muscle, then we have an alternate metabolic pathway where we still produce ATP by converting some molecules in the Krebs cycle into lactic acid. And then lactic acid builds up in the muscle. It starts to bring the pH of the muscle down. And when you get to the point where the muscle pH is too low, the muscle stops working. And it also, you get a burning sensation. So there's pain involved as well. So if you've ever had to hold the shopping bags while you're fiddling for your keys, you start feeling your biceps starting to burn, and that's because you're getting a buildup of lactic acid in the muscles. Typically, the muscles, when they're under tension, the blood flow might not be as good, because when the fibers are stressed, they tend to squeeze together, and it reduces the amount of blood flow passing through them. So you start to build up lactic acid pretty fast. and that's what they call the burn, you know, when you get the lactic acid buildup. And then the lactic acid is metabolized by your liver and other cells in your body to, when you have enough oxygen to breathe. I read somewhere once that in the biochemistry of crocodiles, their muscles are so powerful that after they've struggled to bring down a prey, they can have a lactic acid. They get an oxygen debt that it takes them 2 hours of faster breathing to pay back, as it were. Like we breathe quickly for a few minutes and then we calm down. But so these massive, powerful animals like crocodiles seem to have a much more extended range of capacity. They're highly evolved, of course. Part B. Same amount of energy, 8.9022 kilojoules, divided by the number of moles of lactic acid. So we have to find out the molar mass of lactic acid, how many grams of lactic acid we have, divide those two, and we get the moles. So we're going to say 0.5865 grams of lactic acid, divided by the molar mass of lactic acid, which has 3 carbons in it, weighing 12.011. It's got 6 hydrogens weighing 1.00794. Whoops. And it's got 3 oxygens weighing 15.394 grams per mole. What that works out to is negative 1.36726317 times 10 to the power of 3 kilojoules per mole of lactic acid burn. And you're only allowed, I think, 4 significant figures. 4, that's 5. Yeah, 4. So we're going to say negative 1,367. The book says negative 1,370, but the book is wrong. There's 4 sig figs. 370 kilojoules per mole. I should have put 4 there too, but okay, well, you can fix it if you want. Now, any questions so far? Whose Wi-Fi cut out? Oh. Well, you can text her and tell her that I'm going to put the lecture up tonight anyway, so she'll be able to watch it then. Because I'm recording it on my phone as well. Tell her not to worry. And I'll mark her present. Yeah. Oh yeah, for sure. If you come to class with questions, when we meet person to person, you know what? First of all, there's gonna be like 3 of you. So you're getting private school level of education. So come with questions. I'll explain everything if you want again, because I know this stuff is hard. Plus, you're gonna get a photocopy of the book, so you'll be able to read through it. Because right now you're just going cold. You're just going on what I'm giving you. When you have access to the text, it should help. But we'll go through it again, and you can ask me questions, and just remind me, and I'll do a little review for you. Okay? You're welcome. Now, the next thing we address is a bomb calorimeter. It says, because a bomb calorimeter does not allow the gas to expand, because you have constant volume conditions, if you recall, okay, Stephen, that's all right. I'll still record every lecture anyway. He was saying that he's fully online. That's fine. I record every single lecture, whether or not there's people in the classroom. That's the plan. Because it's good in the long run too. You know, you have access to these lectures. And what I've started doing too today is...
Mr. Alleluia, please call extension 6001. Mr. Alleluia, 6001.
What I've started doing with the recorded lectures that I'm putting on YouTube is time stamping them. So you can go to the little blog at the bottom there, the instructions under the video, and it tells you what I'm doing at each point in the video. That way you don't have to watch an hour of video to find the part that's interesting to you. You can go, just click right, you go right to it. So what was I saying? I was saying about a bomb calorimeter. What is a bomb calorimeter? It's a device they use for finding out how much heat energy can be put out by any given substance. You ever wonder how they find out the number of calories in your food? That's what they do. They burn the stuff. You burn it completely, and the amount of heat that's released by the food when you burn it is the same as the amount of energy that that food will release when your body oxidizes it slowly through metabolism. Because our metabolism is a form of oxidation, but so is burning. Burning is a form of oxidation. Metabolism is a form of oxidation. The only difference in metabolism is it happens much more gradually, and it's mediated by enzymes, and it's a biochemical process, very highly complex and evolved over the course of millennia or millions of years. And of course, God's hand was in there, so don't get me wrong. I don't think evolution answers all the questions. Definitely God's finger was in there, because it's such a highly complex system, and there's no way you could invent something like that to work perfectly from the start, other than by having completely planned it right from the start. It's like trying to say, okay, you know, if you jumble some parts made of metal, you get a Lamborghini at the end. Well, good luck with that. But that's what some evolutionary biologists will have you believe, that somehow atoms colliding with each other turned into enzymes, and enzymes turned into enzyme complexes, and enzyme complexes turned into organ systems, and organ systems turned into complete creatures. I don't buy it. God's finger was in there. He interfered in the affairs of creation, and that's why it's called creation. Anyhow, in a bomb calorimeter, what they do is they take a very thick-walled steel container with a screw top. They put whatever they want to find out how many calories it contains into it. They close the top, and then they inject oxygen at a high pressure, up to about 35 atmospheres of pressure of oxygen. Then they have a spark plug in there as well that screws in tightly, so there's no loss of gases, and they make a spark. And when they make a spark in there with that high concentration of oxygen under pressure, everything that's in that calorimeter burns to a crisp. It turns into ash. And it releases all the energy that is latent within it. All the internal energy is released and has nowhere to go, because the gas is not allowed to expand. Because the gas is not allowed to expand, it can't do any work. So the only way it can manifest that energy is by raising the temperature inside the calorimeter. And that temperature increase is captured by the fact that the thing is immersed in water, so the water warms up, and by the amount of warming in the water, they can do a calculation to find out how much energy was contained in the stuff that was burned inside the calorimeter. So that's how they do that. So a bomb calorimeter, because it's a constant volume vessel, basically measures both enthalpy and the P delta V work. But the P delta V work is not allowed to happen. It just turns into more heat. So really what you're measuring is the internal energy of the stuff inside the calorimeter. Although you're taking an enthalpy measurement, what you're really getting is an internal energy measurement, because all the P delta V, what would have been P delta V work, actually turns into heat energy. So that's the concept of the bomb calorimeter. I had a professor in university who did research with bomb calorimeters, and those things are dangerous, because if you overcharge them, or if you put too much of oxygen or whatever, if the thing is defective, they can explode. And this teacher was missing these fingers. All three of these fingers were gone. He only had his little finger and his thumb, because he was holding the thing and it blew up in his hand. And he was tattooed. He had all kinds of funny colored marks on the skin of his face, because the explosion hit him. And amazingly, he wasn't deaf, so it must have been, I guess, for whatever reason, it didn't make him deaf. He was my physical chemistry teacher. He died, 20 years ago. But I was always sort of shocked to hear the story about how this freak accident happened. I never found out all the details of it, but it was very interesting. Anyway, so let's do page 189 is the next thing. It talks about Hess's Law. Now, Hess's Law, what they do in Hess's Law is they might know the heat of formation, the heat of a reaction. They might know how much heat a certain reaction gives off. And they might also know the heat of several reactions, but they might not know the heat of reaction that is actually the sum of the two other reactions. But they can, by inference, find out what the heat of the third reaction is by adding the other two. And this is the concept of Hess's law. In a nutshell, if a reaction is carried out in a series of steps, delta H for the overall reaction will equal the sum of the enthalpy changes for the individual steps. Let me give you a real-world analogy. You can walk up the stairs one step at a time, climb 3 steps, and you're 3 steps up, or you can take one big step and get to the top, to the landing in one shot. You're still at the same height in terms of altitude. And it's the same way with chemical reactions. You can take a certain amount of fuel and burn it completely until it turns all into carbon dioxide and water, or you can burn the fuel partially and it'll go half of the way down, and then you take the byproducts of that reaction and do another reaction with it where it fully oxidizes again, and in 2 steps you've achieved the same result. And you'll notice that the difference in energies between the products and the reactants is the same before and after, whether you do it in 1 step or in 2 discrete steps. This is the idea of Hess's law. If you know the amount of each step, you can add it up to find out the height of the whole thing. Let's write Hess's law down so you can copy the definition. I'll go here. Actually, no, there's no need for that. You can write it right here. I wonder if the board behind us. No, it's not, but okay. I'm going to end up putting this video at the end of the Thermodynamics playlist. I'm going to call it Practice Problems or Practice Examples. That way you can watch it after you've watched all the playlists so that you understand what the concepts are, hopefully. Now, because a bomb calorimeter does not allow the gas to expand, it's called constant volume conditions. The heat transferred corresponds to the change in internal energy. So I'm just finishing the note to what we previously did. Delta E, rather than a change in enthalpy. Which would be delta H. Now let's move on to Hess's law. So Hess's law, I don't know if you put in that third S, if I just put the apostrophe. If a reaction is carried out in a series of steps, delta H for the overall reaction will equal the sum of the enthalpy changes for the individual steps. So for example, if you look at the practice example on page 190, this note, by the way, is on page 189, they show graphite reacting with oxygen gas to form carbon dioxide. So this is the combustion of graphite, basically. And the heated reaction for this reaction is negative 393.5 kilojoules. It shows you another reaction where you can burn diamond. You can burn diamonds. Diamonds are made of pure carbon. If you raise them to a high enough temperature, diamonds burn. I don't know what the temperature is that you have to expose a diamond to for it to burn, but it's not something you want to be experimenting. It would be a very expensive experiment. But you can burn diamonds, and they combine with oxygen, so it's C. You'll say C diamond plus O2 will give you CO2. You can turn a diamond into CO2. Now, if you flip that reaction backwards, you have CO2 turning into diamond and oxygen. So you're making the reaction go backwards. Basically, to have something like that happen, you'd have to bury some carbon to a depth of about 100 miles, and that's where the pressure of the rocks on the diamond will be high enough to make the carbon assume that that particular crystal structure. That's how diamonds form naturally. They can be formed naturally also with chemical vapor deposition. It's a pretty closely guarded secret that diamonds can be grown, but they don't let that kind of stuff out too much, and they certainly don't like people knowing the way it's done, but it can be done. In fact, there are even funeral parlors, believe it or not, that offer a service where they'll take hair from your loved one, compress it in a giant, well, soccer-sized anvil with a cell inside that you can exert, I don't know how many hundreds of atmospheres of pressure, and they heat it up to thousands of degrees Celsius. And over the course of a week or two, the hair of your loved one, or the carbon in it, will turn into diamond. So you can take the hair of a dead relative, turn it into a diamond ring, mount it, and you can wear the carbon that used to be the hair of your dead relative as a ring. I think it's kind of gruesome, frankly, but for 50,000 bucks you can do it. So here's the reaction. If you flip it around so that CO2 is turning into diamond and oxygen, you'll see a trick we can use to find out the energetics of turning graphite into diamond. See, graphite's on the left over here, but now we're going to take CO2 gas, put it under tremendous pressure, and we will get diamond, and the oxygen would be driven out. I don't think you can do that on the surface of the Earth, and I don't think there are any laboratories that can do that reaction specifically just with pressure. There has to be heat administered as well. Okay, now if you were to add these two reactions together, look what happens. The CO2 cancels, the O2 cancels, and what you get is carbon in its graphite form being turned into carbon in its diamond form. And there's an energy cost. It's not a big energy cost. It's actually plus 1.9 kilojoules. So it's not a huge energy cost in terms of heat, but the conditions for it to happen occur at very high pressures, so it's extremely difficult to achieve because of that, because there's very few materials that can exert a pressure high enough, at least on the surface of the Earth. I mean, we could try, but to achieve pressures that you would see at a depth of 100 miles in the Earth is not something easily achieved in a lab setting. You know those movies where they show people digging into the center of the Earth? That is sheer fantasy. The deepest we've dug into the Earth is 9 miles. That's as far down as we've gone. And if you go deeper than that, the pressure is too high. It damages the drill bits because the temperature starts to go higher. So when you try to drill into the ground into very hard minerals and rocks, the drill bits wear out, first of all, even at normal temperatures. But when you raise the temperature, they wear out even faster. So it gets to a point of no return where you're drilling and you're destroying drill bits one after another and making no progress. So the deepest we've gone into the Earth is 9 miles. It's pretty humbling, because the Earth, to get to the center of the Earth, it's almost 4,000 miles. So all we've done is scratch the surface, and it's like peeling the skin off an apple, basically. So this is Hess's law in application. You have two reactions which you know the heat flux of, the delta H of reaction, and by adding the two reactions, you can find out the delta H for a reaction where you don't have the data, but you can infer it by adding the two reactions. Remember, if you flip a reaction, the sign changes. It becomes, so if I wrote this reaction backwards, where I had the diamond and O2 turning into CO2, it would be negative 395. But because I wrote the other way, it's positive 395. You'll see when you get the copy of the textbook. I wanted to give you, what time is it now? I don't trust that clock on the wall there. It says 1:30. I'm gonna go till 2:30 or till I'm sick and tired of giving you notes, whichever comes first. Practice example, page 191. In this example, it says, it gives you 3 reactions, and it asks you to calculate the delta H for a 4th reaction. So that looks challenging, but it's really not as bad as you might think. I'll show you the answer. Oh, better change the position. Okay. So the first reaction we're going to write as is. Nitrogen monoxide, which is a gas, reacts with ozone, another gas, to produce nitrogen dioxide, a gas, plus oxygen, another gas, and it's balanced. And the delta H for this is negative 198.9. I'm going to put that delta H in kilojoules. The second reaction, which we reversed from what's written in the book, is 3/2 oxygens gas turning into ozone, which is also gas. You'll notice that when I do these problems, I line up my arrows. It makes it easier to do your add your equations. And otherwise, if you make it too messy, that's how you make mistakes. So always line up your arrows. That's just a tip. It may seem obvious to you, but it wasn't obvious to me, and I wasn't very neat in high school. I think that's why I did a lot of mistakes. And the second, so what I did here is I reversed this reaction from what was written in the book. And what I did here was I took half of the reaction and I reversed it to get what I wanted. And how do I know to get what I want? Well, it's something I'm going to have to explain to you in person. I think because you have to be able to see the original reactions. And for now, I'm just going to write you the answer and leave it at that. It's going to require some more explaining. So. So you're going to get 1/2 of negative 495. So I flipped it around. So it's going to be half of that because I also took half of the reaction. It used to be it was 2 O's in the book. Yeah, 2 O's turning into O2, but I only wanted half of it because I wanted to balance off my oxygens, and you'll see how that works out. Once I've got all the balanced reactions the way I want them, I can cancel everything that appears on both sides. So if it appears on both sides of the arrow, you can cancel it out. You can cancel the 3/2O, that's 1.5 oxygens. Here you have 1 oxygen plus another half oxygen. Forgot to put O2. So all that cancels. So all you're left with is NO gas plus O gas turning into NO2 gas, and that was your target equation. And you do the same with the numbers. You add them all up. When you add them all up, what you get is negative 304.1 kilojoules, and that's the answer that the book gives as well. And that's the net reaction. These are actually fun to do once you get the trick. They're not that hard. Don't be intimidated by them. I think it's the marker's getting light. I'll use this one now. Now, it's not just heats of reaction that have been measured. There are many types of enthalpy have been measured and documented in reference books like the Chemical Rubber Company Handbook, the CRC. It's a book about this thick, and they publish it every year since 1904 or something. It's in the 107th edition now, I think. So they started in 1913, I think. Okay? And every year the book gets a little thicker and they add more data to it. So if you're an industrial chemist and you need to know some physical data about different chemicals, that's the book you want to turn to. Nowadays, almost everything is online anyway, but this book has things that you might not find online. For examples of standard heats, there are things like the heat of vaporization, so the amount of energy that goes into turning a certain substance, which is a liquid, into a gas. So different substances require different amounts of heat to be turned into a gas. For example, for water, it takes 2,258 joules of energy for every gram of water to be turned into vapor. And when when that water vapor turns back into liquid water, it releases that same amount of energy. The whole basis of steam engines that dominated the 19th century was the idea of heating up water until it turned into steam, and then to harness the heated steam to pump pistons to move engines as it released that heat energy. The Titanic, for instance, it had either a triple or quadruple expansion engine in it, meaning that it recycled the steam 3 times after the first use. And at the end, it released the steam. So they got the maximum amount of energy from the steam. And they had a whole bunch of men down in the hold of the Titanic shoveling coal to keep the boiler hot, so they could generate steam to keep the ship moving forward. And it was a massive ship, so it took a lot of shoveling. And basically, the steam engine, all through the 19th century, it got better and better. And basically, the engineering that was discovered in the 19th century is what laid the foundations for the internal combustion engine, because it was basically the same mechanism, except now they were burning stuff inside the engine rather than outside the engine, and they were generating steam. But the early steam engines is where we cut our teeth into making engines, and now we have these super advanced engines like the kind you see in race cars. We've come a long way technologically, but we're standing on the shoulders of giants. So you can find heats of vaporization, heats of fusion, which would be the amount of heat to melt something, heats of combustion, which we've just done problems on, and then heats of formation. If you want to make a chemical from all its building blocks in their natural occurring state, you have to do different things to them, like vaporize them, break the molecules apart, and then recombine them to form the molecule that you want. That takes a certain amount of energy. That's called the standard heat of formation. So all these energies are cataloged and listed and available if you want to look them up. I can't imagine why you would, but they're available. And heats of formation, for example, are based on the energy needed to form a substance or the energy released when elements in their standard states are used to form the substance, and they have a big complicated looking equation which I'll translate for you, but let's write that note. It's on page 91 of your text. It's a summary of what you find on page 191, but here it is. Many types of enthalpy have been measured. And documented. Okay. In reference works. Like the CRC, the Chemical Rubber Company Handbook. The CRC for short, it's like the Bible for chemists, which is published yearly. Now, in its 107th edition, I think, in 2020. For examples, of standard heats, there are delta H of vaporization, and you put a knot on there. You put a little circle, like a degree symbol, on the delta H. That means under standard conditions. What are standard conditions? It's all done at 25 degrees Celsius, 1 molar concentration, and 1 atmosphere pressure. Those are considered standard conditions. Delta H of knot of fusion, delta H knot of combustion, obviously standard conditions in the lab, because if you're going to melt something, it's obviously not always going to happen at 25 degrees Celsius. Delta H knot formation.
Miss Nashi, we call extension 6001. Miss Nashi, 6001. Thank you.
If I had a brick. The PA system wouldn't be doing very well now. So when elements in their standard states are used, to form the substance. And the way they say this mathematically is, I gotta move this forward. The way they say this mathematically is the delta H naught, standard heat of for a reaction, is equal to the summation of the number of moles of the heats of formation for the products minus the sum of all the moles of the heats of formation of the reactants. So let me decipher that for you. Standard heat of the reaction, sum of moles of the heats of the, standard heats of formation. Okay, so products minus reactants tells you the heat for the reaction. And you can look up standard heats of formation for practically every chemical known to man, and then from there calculate the heats of a reaction, or at least predict the heats of a reaction fairly well. So the equation above is used to calculate the standard, all substances at 1 molar concentration, 1 atmosphere pressure, and 25 degrees ambient temperature, heat of a reaction from the standard heats of formation of products and reactants. When you get the text, you'll be able to look through that yourselves. On page 193 of the text, are you still with me here? There's a practice exercise on page 193. I'm here on my notes, by the way. Okay, we still have to do this and this, and now we're done. So hang in there. The formation, well, what are they asking in the question? First of all, let's read that. It says, write the equation corresponding to the standard enthalpy of formation of liquid carbon tetrachloride, CCl4. Okay, so the formation equations are written from the constituent elements. So carbon, a solid, reacts with 2 chlorine gas molecules to form carbon tetrachloride, which is a liquid at room temperature. That's your formation equation. In practice example on page 195, they actually make you do a problem where they use that concept. So let's go to page 195, and using standard enthalpies of formation. The book goes through a big long explanation. You can read it yourself, and I hope you do. And it goes without saying, when I give you a handout, and I'll say what my high school teachers neglected to tell me, and which I felt a little bit of rancor for. Obviously, you can't blame other people for your shortcomings. I should have read every single word. I should have been smart enough to figure that out. But I'm going to tell you, just so that you don't have that excuse, read every single word that I give you on the handouts. Otherwise, you cannot plead ignorance as my fault. You have to read all this stuff. It's all in there, but you got to read it. And sometimes can't read it like a novel or a comic book. It's not going to go in here if you read it once. You got to read it 5, 6, 10 times, depending on how good you are at absorbing information. I would have had to read it in some places 10 times before I got what was going on. So you've got your work cut out for you. This is not easy. This is not an easy chapter. I make no apologies for it, folks. I don't want you to go into this thinking, oh, well, I'll figure it out. You got to put your head down and push to get through this material. If you don't have that attitude, it's going to crush you. Page 195 then. Use the standard enthalpies of formation listed in table 5.3. Calculate the enthalpy change for the combustion of 1 mole of ethanol. By the way, if you do succeed in learning something from this, it gives you a good sense of satisfaction. You actually feel good. Your brain likes it when it actually conquers something difficult. It gives you a good feeling. Here's the reaction. You have ethanol. Plus 3 oxygen gas gives you 2 CO2 gas plus 3 H2O liquid. Now I looked up all the standard heats of formation. You're going to have a photocopied section of the book where you can look all those things up, so I'm going to include it with the package I give you. So for now, I looked up all the numbers for you, so here they are. 277.7 for the formation of methanol. Any element in its standard state is going to be 0. For oxygen doesn't require any energy to be formed. It's sitting here in the atmosphere. 21% of what we breathe is oxygen. So the energy required to make oxygen is 0 at the standard atmospheric temperature. And then for CO2, it's negative 393.5 because it's composed of 2 different atoms. And then for water, in liquid form, it's negative 285. And they do specify that there's a difference between liquid and gaseous water. Gaseous water has more energy in it because it's moving around more quickly. So its heats of formation will be different from liquid water. There you go. Now to get for the whole reaction, it's going to be the total energy of the reactants. The total energy of the products minus the total energy of the reactants. So that's what this looks like. So I'm going to write delta H naught of reaction is equal to, I like to make 2 big square brackets, one for the products, one for the reactants. 2 times, and you got to put the balanced numbers, right? There's 2 moles of CO2, so I'm going to say 2 times the amount for the CO2 is negative 393.5 plus 3 times the amount for water, which is a liquid. 3 times 285, negative 285.83. Products, here's the product side, and now the reactants, I'm going to make another big square bracket, and it's just ethanol, which is 277.7. Don't forget to put the negative sign, because it's product minus reactant. So you see that's a double negative, that's going to turn it into plus. And then the oxygen is 0. You can write the 0 in if you like, but it doesn't change anything. What you get at the end, when you add everything up, is negative 1,367 kilojoules. Now on this type of question, you got to be careful with your sign conventions. If the table at the back of the book says negative 393.5, don't forget that minus sign, or else all the stuff you do is going to be garbage after, because you're going to get the wrong number. Here's a question where multiple heats of formation are necessary. Suppose somebody asked you, now you're not going to find this question in the book, I made it up. Suppose somebody asked you how much energy would it take to take 1,000 grams of ice at minus 20 degrees Celsius and turn it into steam at 100 degrees Celsius. So what does it take to do that? You have to first of all warm up the ice until it reaches the melting point, which is 0. So you have to bring the ice from minus 20 to 0. You have to then melt the ice, which happens at 0. That takes a certain amount of energy. Then once the ice is turned into water at 0 degrees Celsius, you got to warm it up all the way to 100 degrees Celsius. Once it gets to 100 degrees Celsius, it starts boiling. But you still have to keep on adding energy until all of the water turns into vapor, because there's energy required to go through a phase change. In fact, it's an energy change. It's a phase change. A phase change takes place without a temperature change. So the water will stay at 100 degrees Celsius until all the water has evaporated. And then the steam will start warming up to a temperature higher than 100 degrees Celsius. But that energy is going to keep on getting absorbed by the water until all the liquid water turns into gaseous water. And because the temperature doesn't change, they call it the latent heat, meaning hidden. Latent means hidden. So it's a latent heat of vaporization, because you're adding energy, but the temperature is not going up. Where's the energy going? Well, it's going into separating those liquid molecules into gaseous molecules so they can be flying around. And that takes energy, because water molecules are attracted to each other. So here's the question that I made up, which would be excellent for building up your understanding of heats of different chemical processes, including phase changes. It's all about energy. I know this is a marathon of notes, but we have to get through this, folks. You're going to university next year, and it's no picnic. Question: how much energy is needed to change 1 kilogram of water, ice, because you can have ice from other chemicals, it doesn't have to be only water, at negative 20 degrees Celsius into 1 kilogram of steam at 100 degrees Celsius. Given that the specific heat of solid water, meaning ice, is 1.76 joules per gram degree Celsius. So it takes 1.76 joules of energy to warm up a block of ice by 1 degree. And the specific heat of fusion for ice, in other words, melting ice, how much energy does it take? It is 333 joules per gram. It takes quite a bit of energy. But, and then the specific heat of warming water, you'll be familiar with, is 4.184 joules per gram degree Celsius. I know I keep on being inconsistent there. Sometimes I write 4.184 and sometimes I write 4.186. I think the average is 4.186 from that range, 0 to 100. But if you go from 14.5 to 15.5, where the original experiment was done, the value is this, 4.184. And that experiment was done by a guy called James Prescott Joule, of Joule's fame. That's why they named it the thing in his. So he discovered the calorie. He was the one who defined the calorie, but then they named the joule after him. Go figure. One more thing we need is the specific heat of vaporization for water. And get this, this is the one that has the most amount of energy necessary. So to turn a gram of water into steam takes 2,258 joules of energy per gram. So it takes a lot of energy to make steam. So let's do the calculation. It's a 4-stepper. First of all, you start with Q is equal to MC delta T. And you have 1,000 grams of water, because they said 1 kilogram, at 1.76 joules per gram degree Celsius, times a temperature change of 20 degrees, because your ice cube was at minus 20, now you're going to bring it up to 0. So you get 3.52 times 10 to the power of 4 joules of energy, just to do that part. Then you're melting your ice. So you're going to use Q is equal to M times C for ice. So 1,000 grams of ice melting at a cost of 333 joules per gram means it's going to take you 3.33 times 10 to the 5 joules of energy. Then you're going to warm up that water from 0 degrees all the way to 100 degrees. So we're going to use Q is equal to MC delta T to calculate that part. So that's 1,000 grams of water at 4.184 joules per gram degree change in temperature. Means you're going to expend, and there's a 100 degree change in temperature. You're going to expend 4.184 times 10 to the 5 joules of energy doing that. So far, the most energy expensive part of the process has been warming up from 0 to 100. Although considering that here all you're doing is melting the ice, that's the amount of energy. So still, that's the most expensive part, getting it to the boiling point. And then the last step is to turn that hot liquid water at 100 degrees Celsius into steam at 100 degrees Celsius. So that requires a further input of energy. We're going to calculate that using the heat capacity, not the specific heat capacity of 2,258 joules per gram. So you get 2 million 258,000 joules of energy necessary for that. And that's by far the most energy expensive part of the process. Now, if you add up all these four things together, the total is 3,044,600 joules of energy to warm an ice cube from -20 to 100 degrees Celsius steam. Or if you want to, you can rewrite it as, remember, 1 megajoule is equal to 10 to the power of 6 joules. So it's basically 3.04 megajoules of energy. 3.04 million joules. So the steps, again, to recap are: 1, warming the block of ice; 2, melting the block of ice; 3, warming liquid water from 0 to 100; 4, the water boils, turning it to vapor, so the temperature stays at 100 degrees during this time, which is step 4. That's vaporizing the water. So something I said already, I'll say it again by reading what I have in my note here. I don't feel like writing it out now. During changes of phase, energy is inputted or released, but without a change of temperature. This apparent contradiction led to the energy change inherent to the phase changes being called latent heat or hidden heat. Example, here I'll make a sentence using the word. Latent heat of the latent heat of vaporization of water is 2,258 joules per gram of water vaporized. Last thing is the sample problem from practice example on page 196. Now we are at 2 o'clock, so we're going to finish a little early. By now you're probably head down on your desks with a little stream of drool coming out of your mouth, but we got to do this. Practice example, page 196. So for this reaction, the heat is 129.7. What they're asking us to find out is the heat of formation for that thing. Now, I accidentally looked it up, so I knew it, but I'm going to put X there. Okay, we'll call this X. Pretend we don't know it, although you can look it up in the book. This is 0 because it's hydrogen gas and it's standard state. Copper is a metal at room temperature, so that's also going to be 0. Liquid water is a compound, so it necessarily is going to have a non-zero quantity. So we're going to see a simplification of that big equation with the Greek letter E, sigma, and then the N, and the delta H naught of formula. I put that all into this. Delta H of the reaction is equal to delta H naught of the products minus delta H naught of the reactants. Okay, don't use that big formula. You don't have to write all that out. We understand you have to keep the moles and all that in track of them. So let's write the numbers down. So the whole reaction is 129.7. Open big bracket for products. It's negative 285 for the water in the liquid state, mind you, and 0 for the copper. So we're just going to put plus zeros so that we give assent to the fact that we've included the copper, but it's 0, so it doesn't do anything. And then the copper oxide is X. We don't know it, but we can look it up in the same table and we'll know what it is, and then we can check our answer anyway. And then 0 for the hydrogen gas. When you run through this whole equation, you're going to get this. Negative 129.7 is equal to negative 285.83 minus X. Now be careful when you don't know what X is, but you know that products minus reactants is what's happening. So you're going to have to put minus X when you distribute that minus sign into the bracket. What it works out to is, if you transpose that 285, you're going to get 156.13 equals negative X. Don't lose that negative sign or else you get the wrong answer. So the answer is X equals negative 156.13 kilojoules, and sure enough, if you look it up, that's what you get. And you're only allowed 4 sig figs, so we have to report 156.1 kilojoules. And that's it for today. For your homework, I'm going to post this video. It's an hour and 15 minutes long. Anything you missed in what I did today, you can follow up, and I'll try to index the video over the weekend so you can get to the parts that are important to you. And also finish watching the rest of the Thermodynamics playlist. I think there's 7 parts to it. Now, by this weekend, it's going to go to 9 parts, because I'm going to add the video I did yesterday and the video I did today. So you got plenty of watching pleasure there. So use your time well. And now I will take attendance. If you have any questions, feel free. I don't have my pencil.